Okay, we're back with a specific example involving all of these connections. I left a couple on the board. I had to erase the others, but those were the easier ones to work with. So here we go. We have a graph on the board. You can see that this graph is just a polynomial graph. It's got some hills, it's got some valleys, it crosses the x-axis for the first time at -4 and for the final time at 4, okay? Now, the key thing to know about this problem is that we are looking at the graph of the derivative of f, okay? We have no idea about f, the function. All we know is a picture of the derivative of the function. But we're going to use this data to answer these questions right here about the function. So, we're given the graph of f prime, which is the derivative of f, and we want to know on which interval or intervals is f increasing. Okay? So again, you can't believe your eyes right away. The first thing we want to do, oh, function's increasing, that means it's going up. So we start looking, when is the function increasing? When is the function going up? We don't want to do that right now, though, because we're not interested in when the derivative is increasing. We're interested in when the function is increasing. And we know at this point that a function is increasing when the derivative of the function is, yes, positive. Okay, so when is our graph positive? That's what we're looking for. Well, it's definitely positive between -4 and -2, and it's definitely positive between 0 and 2, and it's definitely positive after x equals 4. Those are our three intervals in which f is increasing. Okay, -4 to -2, 0 to 2, and 4 to infinity. Okay, now, we've written that down, but here's the even more important thing to write down. The answer to the question, why? Why did we pick these three intervals? Yes, because the derivative is positive. So, -4 to -2, 0 to 2, 4 to infinity, because f prime was positive. We want that reason down on the paper. They're going to question you on that. You need to know the reason why as much as being able to identify the actual interval or values of x. Okay, when is the function concave down? That's what we're dealing with right here. If we had a second derivative graph, we would look and see when the second derivative was negative, but we don't have a second derivative graph. We have a first derivative graph. And therefore, we need to look and see when is the first derivative decreasing. Okay, so now we go to our graph. We have to see the graph going down from left to right. So from -3 to -1, and from 1 to 3. On those two intervals, the graph of the derivative is decreasing. Therefore, the function will be concave down. So from -3 to -1, and also from 1 to 3. On those two intervals, and again, I've written these intervals using the parentheses, brackets notation. You can write them with the whole less thans and everything, that's fine. But either way, you just want to get an interval down. Okay? Again, why? Because the graph of the derivative is decreasing. Okay? Because, all right, so that's our, I'm going to stop writing because and do my triangle again. Because f prime is decreasing. Okay? All right, next up. For what value or values of x does f have a relative minimum? Okay, so that's from previously. A relative min occurs when the derivative changes from negative to positive. So if we look at our graph, that's a change from negative to positive. That's a change from positive to negative, so we're going to ignore that one. Here's a second time that we have a relative min, and we have a third one right there at 4. In those three cases, those three values of x, the derivative changes from negative to positive, which means we have a relative min. All right, so x equals, again, this is not an interval now, it's values of x. So x, we said -4, and then again at 0, and then again at 4. So -4, 0, and 4. Why? Because f prime changes from negative to positive. Negative to positive, and hopefully that's still on the screen there. I can't see. Yeah, it does. Okay, so there's our reason. Okay, and finally, for what value or values of x does the function have an inflection point? Okay, so an inflection point of inflection, occurs when f prime changes from increasing to decreasing or decreasing to increasing. In other words, when f prime has a relative extreme, when it has a relative max, or when the derivative has a relative min. So we're looking at the top of the hills and the bottom of the valleys. All right, so -3, -1, 1, and 3. In those 4 spots, the derivative changed from increasing to decreasing or decreasing to increasing. Okay, so when that specific incident happens, we have ourselves a point of inflection. So we said x equals -3, and then -1, and then 1, and then 3. Those 4 values of x are where the function will have an inflection point. And the function will have an inflection point because f prime changes from increasing to decreasing or decreasing to increasing. Okay, so we can gather up all this information about the function based off of the data from the derivative of the function. And that's, again, a key thing that's going to come into play over and over, not only for the rest of this year, but also on the exam.